Module 4 Principal Stress Mohs Circle. In this module, we will be seeing how to derive the stress on any inclined plane inside the material with a given system of loading. That is, while we're discussing about the state of stress at a point, we have seen the example of a specimen loaded by load P on both sides. Then what we have seen is, if we take a cross section, we take a small element here. What are the stress acting on that element? That is called the state of stress. And we have seen that the stress acting on this element is given by sigma is equal to P by A. And if the coordinate directions are like this, x and y direction, we have sigma x equals P by A. Sigma y is not there, and tau xy is also not there. So this gives the state of stress of the element. This we have seen in the first module. Now, what will be the state of stress of an element which is inclined to the axis? That is, for same loading system. Instead of taking a plane like this, now I am taking a plane which is inclined by an angle theta. I take a small element like this. So initially you have your element like this. Now the element is tilted like this. What will be the stresses acting on this element? This we can show it in this way. This we have already seen in strength of material. This is only a recap. If this angle is given by theta, sigma x is the stress in the x direction, sigma y is the stress in the y direction, and tau xy are the shear stress acting. Then we have sigma theta as a normal stress acting on the plane. Sigma theta is the normal stress acting on the inclined plane. And tau theta is the shear stress acting on the inclined plane. Now, here we are interested in finding what is sigma theta and tau theta. Since this element is in a case of static equilibrium, we have the necessary conditions of equilibrium. That is sigma fx 0, sigma fy 0, and sigma m is equal to 0. If you do the force equilibrium for this kind of element, we get, and if you resolve all the forces in the theta direction, if you resolve all the forces in the sigma theta and tau theta direction, then we get sigma theta as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Similarly, tau theta will be given as minus of sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. This is an important equation. This is called the stress transformation equation. Stress transformation equation is nothing, but what we are doing is, knowing the state of stress in one plane, we are trying to find the state of stress at another inclined plane given by angle theta. We are transforming the stresses from this plane. We have the stresses. We are transforming it to the another plane which is inclined at angle theta. So this is called the stress transformation equation, and sigma theta and tau theta are the normal stress and shear stress acting on the plane which is inclined at angle theta to the y direction. So we see that This is already discussed in strength of material, so I am not going into much detail of the derivation. From these two equations, sigma theta and tau theta, what we understand is sigma theta and tau theta is varying with theta. That is, as theta keeps on changing, your sigma theta and tau theta also changes. That also keeps on changing because it is having a sigma theta and tau theta are having a function of cos 2 theta and sin 2 theta. So when the theta keeps on changing or keeps on increasing, sigma theta and tau theta keeps on changing. And we can see that for one particular value of theta called theta p, the normal stress becomes maximum. This plane at angle theta p is called principal plane, and the maximum normal stress acting on this plane is called principal stress. And it is found out that on the principal plane, shear stress becomes equal to 0. So what we do is, in this equation, we keep on increasing the value of theta and plot sigma versus theta. That is, we'll draw a diagram between theta and sigma. Similarly, theta and tau theta, sigma theta. From this, what we see is, it keeps on changing, and at one particular value of theta, sigma theta becomes maximum. It's called the normal stress, maximum normal stress or principal stress. Similarly, for another value of theta, you get a maximum shear stress also. So we can also find out that tan 2 theta p, if theta p is a principal plane, tan 2 theta p is given by 2 tau xy by sigma x minus sigma y. This is the principal plane, or the angle of the principal plane with the y-axis is given by tan 2 theta p, given as 2 tau xy by sigma x minus sigma y. This value of angle theta, if we substitute in this equation cos 2 theta and sin 2 theta, we get the value of sigma theta. That is nothing but the maximum and minimum principal stress. From this equation, we can see that tan 2 theta p has got two positive values. So theta 2 theta p can take two values. Takes two values. One in the first quadrant and another in the third quadrant. Because tan theta is positive in the first quadrant and third quadrant. For one tan theta, you have two angles. Like if tan 2 theta p is 1, then I have 2 theta p. If, for example, if tan 2 theta p is suppose 1, I can say that 2 theta p is equal to 45 degree or 225 degree. Both are possible solutions of this 2 theta p. So from this I can say theta p will be 22.5, 112.5. So there will be two value of thetas. So for each value of theta, you will get a sigma theta. So therefore you will be getting two values of sigma. One is called sigma 1 and another one is called sigma 2. These are the principal stresses. For theta p1 and theta p2, I'll call this theta p1, this as theta p2. And if you substitute this value of angle 2 theta p in the shear stress equation, then it becomes 0. Therefore, we can say tau theta p is equal to 0. This is about the maximum normal stress, or called the principal stress. I have also told that when theta p keeps on changing, your maximum shear stress also keeps on changing. That is, tau theta also keeps on changing with theta. And there's one value of theta called theta s, at which the shear stress is maximum. And we can say tan 2 theta s is given as minus of 2 tau xy by sigma x minus sigma y. And this is at, therefore 2 theta s is equal to 2 theta p plus 90 degree, or theta s is equal to theta p plus 45 degree. Or I can say maximum shear stress plane is at an angle of 45 degree to the principal stress plane or principal plane. So now we'll try to see some application of this equations. Now we'll see an application of this equations of principal stress and maximum principal planes and maximum shear stress. That is given a loading system, how to find the principal stress and principal planes. This is very important, because for any given loading system, the maximum normal stress will not be the normal stress given here. Will not be the stress in the state of stress, but will be a different value. We will illustrate this by an example. For this, see this problem. We have a rectangular body which is subjected to a loads given by sigma x given by 80 Newton per mm square and sigma y given by 40 Newton per mm square, and x and y direction are shown here. So here we have that sigma x equals 80, sigma y equals 40. Now we have to find what is the stress sigma theta and tau theta acting at an angle, acting on a plane at angle theta is equal to 20 degree, shown here. That is, if this is the angle theta 20 degree, what is the normal stress and shear stress acting on this plane? This I can show this way and this way. What is these two values? Now we have sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. So this will be given by 80 plus 40 by 2, that is 60, plus 80 minus 40 by 2, I'll write it clearly, 80 plus 40 by 2 plus 80 minus 40 by 2 into cos of 2 theta, so 2 into 20 degree, plus tau xy. What is tau xy? Tau xy is equal to 0 for this loading condition. So this will be equal to 80 plus 40 is 120 by 2 is 60, plus 80 minus 40 is 40 by 2, 20 cos 40 degree. This will be how much? This will be 75.32 per mm square. This will be the normal stress acting on this plane. And similarly, what will be the shear stress acting on this plane? That will be given as minus of sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. Now we will substitute these values. We get minus of 80 minus 40 by 2 into sin of 40 degree or 2 into 20 degree plus tau xy is 0. So this becomes equal to minus of 40 by 2 is 20 sin 40 degree. That will be given as 12.87 Newton per mm square minus, so I can say my sigma theta equals 75.32 Newton per mm square tau theta is equal to minus of 12.87 Newton per mm square. Now, okay, now if we are asked to find what is a principal plane, how we can find that? The principal plane is given by tan 2 theta p is equal to 2 tau xy by sigma x minus sigma y. This is equal to 0. So I have 2 theta p is equal to 0 comma 180 degree. So my theta p will be 0 comma 90 degree. That means what? At two planes I have the principal planes. That is, if suppose this is the body with 80 and 40, what this says is this plane where theta is equal, for this plane theta will be 0 degree, because theta is what? Theta is the angle from the y-axis. So if this is the angle theta, theta is equal to 0 means I have this plane, and for theta is equal to 90 degree I have this plane. So from this what we can see is theta is equal to 0 degree is this plane, theta is equal to 90 degree is this plane. So the principal stresses are acting on this plane and this plane. So 80 and 40 are nothing but the principal stress themselves. Okay, so here we have sigma 1 is equal to 80 and sigma 2 is equal to 40. So what will be a tau max? Tau max also can be written as sigma 1 minus sigma 2 by 2. It will be 80 minus 40 by 2. That's equal to 20 Newton per mm square. This way, for any given loading system, for any given loading system like this, with a given value of sigma x, sigma y and tau xy, we can find what are the stresses acting at any plane inclined diagonal theta with the y-axis. Also we can find what is the principal plane, what are the principal stresses, and what is the maximum shear stress, and what is the plane on which it resides. So what will be theta s? Theta s will be theta p plus 45 degree. That will be, theta p has two values, 0 and 180 degree. So theta s will have two values, 0 plus 45 degree. That is nothing but 45 degree, and 0 plus 135 degree. That's nothing but 135 degree. So maximum shear stress will be acting at a plane which is inclined by angle 45 degree. So how do we show that? I'll draw it here. So if this is my normal, this is the plane on which I have 80 and 40 acting, the problem says, then if I rotate this plane by angle 45 degree, if this angle becomes 45 degree, then I have the shear stress acting as maximum. This for this plane, the tau will be equal to tau max. So by this you will be clear how to find the principal stress, principal planes, maximum shear stress, also how to find the normal stress and shear stress acting on any plane inclined angle theta to the y-axis. Now let us take another example where instead of giving sigma x and sigma y, directly it's given the principal stresses. Principal stresses sigma 1 and sigma 2 are given, and we are asked to find what is the normal stress and shear stress acting on a plane inclined angle theta to the y-axis. Here it is given theta is equal to 60 degree to sigma 1, that is x-axis. So what will be the inclination to the y-axis? Inclination to the y-axis will be 90 minus 60, that is 30 degree. That is, what is given is this angle. This angle is given as 30 degree, 60 degree. But in our derivation we have seen The angle which we are using is the angle inclination with the y-axis. So we'll be interested in this angle. Therefore, the inclination of the plane with y-axis is 30 degree. So given sigma 1 and sigma 2, we want to find the normal stress and shear stress acting on the plane inclined angle theta is equal to 30 degree. How do we do that? Now we are given, here we are given principal stresses directly. So what we can say about sigma x and sigma y? Suppose this itself we can, since it is given as principal stresses, we can take it as a condition where sigma x is equal to sigma 1, sigma y is equal to sigma 2, and tau xy is equal to 0 because it's a principal stress. If the principal stresses are given, then the shear stress on the principal planes will be 0. So we have the condition as sigma x is equal to sigma 1, sigma y is equal to sigma 2, and tau xy is equal to 0. For this for this problem we have sigma x is equal to sigma 1, which is nothing but 200 tensile. Tensile means it is positive. What is sigma y? Sigma y is equal to sigma 2, that is 100 compressive. Compressive means you have to take it as negative. And tau xy is 0. So what is sigma at angle theta? Will given by sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. So what we can say here, it will be, here you have to be very important about the sign. If it is a tensile force, we take it as a positive. That is, if the stress is tensile, we take it as positive. If the stress is compressive, we have to take it as negative. So here sigma y is minus 200. This is very important. Sigma y is minus 100 and sigma x is plus 200. So we have 200 minus 100 by 2 plus 200 minus 100 by 2 cos of 2 theta. Theta is equal to 30 degree. So we have a cos of 2 theta is 60 degree plus tau xy is 0. So this becomes 50 plus 150 cos 60. There will be a sigma theta. This is equal to 125 Newton per mm square. Similarly, what will be tau theta? Tau theta will be minus of sigma x minus sigma y by 2 sin 2 theta plus tau xy cos 2 theta. So this will be here 200 minus of 100 by 2 sin 60 degree plus 0. That's equal to 150 sin 60. That will be 129.9 Newton per mm square. This way we can find what are the stresses acting on any plane inclined angle theta to the y-axis. So here if we are given the principal stress as 200 and minus 100, so what will be the maximum shear stress? Maximum shear stress will be sigma 1 minus sigma 2 by 2. That's equal to 200 minus of 100 by 2. That's nothing but 150 Newton per mm square. In the derivation of principal stresses, we have seen that sigma theta is given by sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Then we found out that tan 2 theta p will be the principal plane given by 2 tau xy by sigma x minus sigma y. And also we have seen that this theta p is going to have two values. So there is two planes we'll get, and the stress acting on one plane is the will be first principal stress, and the stress acting on the second plane will be the second principal stress. So if these two values of theta p are substituted into sigma theta, you get sigma 1 is equal to we'll get the principal stresses sigma 1 and sigma 2. And the maximum shear stress we can find out by this relation given by sigma 1 minus sigma 2 by 2. This on substitution of this tan 2 theta p is this value. This value of angle, if we substitute in this equation sigma theta, we can get sigma 1 is equal to sigma x plus sigma y by 2 plus square root of sigma x minus sigma y by 2 whole square plus tau xy square. And sigma 2 will be sigma x plus sigma y by 2 minus square root of sigma x minus sigma y by 2 plus tau xy square. And we know that tau will be equal to 0. Similarly, we have seen that tan 2 theta s is given by minus of 2 tau xy divided by sigma x minus sigma y. So this value of angle, if we substitute in sigma theta and tau theta, we'll get another value of sigma and tau. And that maximum value of shear stress which we get will be given as square root of sigma x minus sigma y by 2 whole square plus tau xy square. And sigma 1, sigma 2 can be written as sigma x plus sigma y by 2 plus or minus square root of sigma x minus sigma y by 2 whole square plus tau xy square. So from this equation we can get that tau max is equal to sigma 1 minus sigma 2 by 2. Now another example we'll take. A rectangular specimen is subjected to a load such that sigma x is equal to 20 Newton by mm square, sigma y is 10 Newton by mm square, and we have a shear stress also, tau xy, which is nothing but 10 Newton by mm square. Now we have to find what are the principal stresses, and what is the plane on which it acts, and what is the maximum shear stress, and what is the plane on which the maximum shear stress also acts. So first what we can do is, for this given condition, we can write out sigma x is equal to 20, sigma y is equal to 10, tau xy is equal to 10. Now first we find out what is the plane on which the maximum shear stress, maximum normal stress will be acting, or the principal plane, which is given by 2 tau xy by sigma x minus sigma y, that's equal to 2 into 10 20 divided by 20 minus 10, that's equal to 2. So tan 2 theta p is equal to 2. So we'll have two angles corresponding to the tan 2 theta p is equal to 2. That is tan 2 theta p is equal to 2 will give two values of 2 theta p, which are nothing but 63.4 degree and 243.26 degree, which further gives that the principal planes sigma theta p will be equal to 31.7 degree and 121.43 degree. So we have got the two values of principal planes. First principal plane is 31.7 degree and second one is 121.43. So what will be the stresses and maximum normal stress acting on it? We have the equation sigma theta is equal to sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. Here we can substitute the values 20 plus 10 by 2, that is 30 by 2, that is 15, plus 20 minus 10 by 2, that is 5, cos. We will put the first principal stress, that is sigma theta sigma 1, the cos of 31.7 degree, plus tau xy, that is 10 sin 31.7 degree. This will come out to be 26.18 Newton per mm square. Sigma 2 will be 15 plus 5 cos, instead of 31.7 we will have 121.43 degree plus 10 sin 121.43 degree. This will become 3.82 Newton per mm square. So that is the principal stresses sigma 1 and sigma 2. And therefore what is the maximum shear stress? Maximum shear stress will be given by sigma 1 minus sigma 2 by 2. That is equal to 26.18 minus 3.82 by 2. This will be 11.18 Newton per mm square. And what about the planes on which it is acting? So what I can say is, if this is the state of stress of the body which is given here, sigma x, sigma y and tau xy, this is the element, sigma x is equal to 20, sigma y is equal to 10 and tau xy is equal to 10. If this is the case, then I can find the element inclined by an angle 31.7 degree. I can draw element like this in that body. If I take that element outside, I will draw that element here. What will be the stresses acting on it? It will be nothing but sigma 1 and sigma 2. And what will be the shear stress? Shear stress will be 0 because this is a principal plane or the maximum normal stress plane. So if I take a element which is at an angle of 31.7 degree, then I will be having only normal stress acting on this element. And the normal stress maximum will be sigma 1 and the minimum will be sigma 2. Similarly, if I rotate it by again another 45 degree, if I rotate this element by another 45 degree, like this, or if I draw that element like this, what will be this angle? This angle theta will be 31.7 degree plus 45 degree. If I take this plane, what I will have my shear stress as the maximum shear stress. The tau will be equal to tau max. But what will be the sigma acting here? Very important thing is, the very important characteristic of the principal plane is that on the principal plane, the normal stress is maximum and shear stress is 0. Normal stress maximum is given by sigma 1 comma sigma 2. And the plane on which it is given by sigma theta p1 and theta p2. For maximum shear stress plane, we can say that tau theta is maximum. But contrary to what we see in principal plane, where the sigma theta is maximum and shear stress becomes 0, in maximum shear stress plane, the shear stress is maximum, but sigma theta will not go to 0. Sigma theta is also a definite value. That is, there will be a value of a normal stress, but it will not be a maximum normal stress. But there will be some value for this normal stress. This plane is given by theta s. So the normal stress will still be there, but it will have a value. It will not be 0. So that is a property of this maximum shear stress plane and the principal plane. So we can see, we have seen that for given loading system, we can find out what is the maximum normal stress or the principal stress, and the plane on which it is acting, it's called a principal plane, and what is the maximum shear stress, and what is the plane on which the maximum shear stress is acting. So with this much of concept, we should be able to predict what is the normal stress in a given loading system. We will see one more illustration of this principal stress. Now we will take another example where sigma x, sigma y and tau xy is given, and we have to find what is the principal stress plane or principal plane, maximum shear stress and the maximum shear stress plane. So what we can write is sigma x is given by 100, sigma y is 50, tau xy is 60. So this is also a direct substitution of the stress values. So first we have to find what so how to find the principal stress. First we have to find what is the principal plane angle, or the angle, the plane at which the normal stress principal stress are acting. That is given by tan 2 theta p is equal to 2 tau xy by sigma x minus sigma y. That's equal to 2 into 60 degree 60 divided by 100 minus 50. This is equal to 120 by 50. So 2 theta p will have two values. Will be one value will be 67.3 degree. Second value will be 247.3. So we have theta p will have two values, 33.69 and 123.69 degree. So these are the two planes, principal planes, theta p1 and theta p2. That is, if one plane, so I can draw the plane as this. This will be 33.69. And this angle will be 123.69. So you have sigma 1 here, sigma 2 here. So your sigma 1 is given as sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. So substituting the values, sigma x is 100, so 100 plus 50 by 2 plus 100 minus 50 by 2 cos. So I will find the first principal stress, which is acting on the plane 33.69 degree, 0.69 degree plus tau xy is 60 sin 33.69 degree. This will be 75 plus 25 cos 33.69 degree plus 60 sin 33.69 degree. This will come out to be 140. What will be sigma 2? Sigma 2 will be the same, but the angle will be different. Cos of, instead of 33.69 degree, now we have 123.69 degree plus 60 sin 123.69 degree. That will be, if you calculate it, it will come out to be 10 Newton by mm square. So what will be the maximum shear stress? Maximum shear stress will be sigma 1 minus sigma 2 by 2. You have already seen this. That will be 140 minus 10 by 2. That's equal to 65 Newton per mm square. And what will be the plane on which the maximum shear stress will be acting? Theta s. Theta s is nothing but theta p1 plus 45 degree. That is nothing but 33.69 plus 45 degree. That's equal to 78.69 degree. That is, if I take if this is my x-axis, if I take another element like this, where theta is equal to 78.69 degree, then I can say the normal stress, the shear stress will be maximum. And what will be the normal stress acting on this plane? That also we can find. So I can write normal stress acting sigma theta s will be, have the equation sigma x plus sigma y by 2 plus sigma x minus sigma y by 2 cos 2 theta plus tau xy sin 2 theta. But here what will be the value of theta? Theta will be 78.69 degree. So that will come out to be 75 plus 25 cos 2 theta 2 into 78.69 plus 60 sine 2 into 78.69. Sorry, here I made a small mistake. This is actually not 33.69. It is 2 into 33.69 degree because it is 2 theta. Similarly, here also it is 2 into 123.69 degree. Pardon me. Because the equation is 2 theta here. So it will be 2 into 33.69 degree. So what will this come out to be? It will be 75 plus 25 cos 2 into 78.69 plus 60 into sine 2 into 78.69. That will be 75. So I can say for this element here, given here, the shear stress is maximum. That's equal to 65 Newton per meter mm square. And the normal stress is also acting here. $75. For this plane it will be 75 Newton by mm square. For this plane, again the angle will be different. So this will be 75. This will be different. It will be for that it will be angle will be, let's S1 and S2. Angle will be 78.69. -90 minus 78.69. That is this angle. So if you substitute that value, you can get a value of sigma. That means when the shear stress is maximum, that plane will also have a normal stress. Normal stress will not go to 0. It will have a different value of a normal stress also. But for principal planes, you have normal stress is maximum and the shear stress becomes 0.